Hello everyone and welcome to this 10th video that will be part of the series about abstract algebra. And today we're going to continue our discussion about permutation groups and permutations in general. In particular, we will start by looking at what is known as cycle notation. So we're gonna write it here. And so in the last video we've seen how we can represent permutations by using those array notations. So for example, a permutation, alpha, we can write as alpha, for example, of a set 1, 2, 3 that can be written, for example, as follows. So you can have the original ordering of the set that you're considering on the top, and then on the bottom you will have the images of each of the corresponding elements. But we can also represent these permutations in another way that very often, and we will see why, and we will prove some results later that will convince you that this is actually a good idea. We can actually write it in terms of cycles. But what is a cycle exactly? A cycle, like the word suggests, is something that goes back to itself. And so what we can do is we can basically reduce this permutation to a product of stuff that goes back to itself. So in order to do this, I think it will be immediately clear once I provide an example. So for example, consider the following permutation beta that sends the set 1, 2, 3, 4, 5, then sends 1 to 3, for example, then 2 to 4, then 3 to 5, then for example 4 to 2, and 5 to 1. Okay, so now let's picture this a little bit more graphically with arrows. So what this permutation does is it sends 1 to 3, so we can say 1 gets sent to 3, then 3 gets sent to 5, and well, as you can see, then 5 gets sent back to 1. Well, this is precisely a cycle. And so how can we represent the cycle? Well, graphically, we could represent the cycle as something like this, for example. So 1 goes to 3, then 3 goes to 5, and 5 goes back to 1. Another cycle of this permutation is the following. Well, 2 goes to 4, but then 4 goes back to 2. And so this is again a cycle, and we can picture as follows. So for example, like this. And we have just decomposed this permutation into cycles. So we can also write this permutation beta in terms of these two cycles. And however, as you can see here, using these diagrams, and also using these arrows here, is a little bit expensive in terms of spaces. So what we do instead is we write these cycles in the following way. So you take the cycle 1 that gets sent to 3, that gets sent to 5, and then 5 that gets sent back to 1. We can write it as just 1, 3, 5. And in the same way, this cycle here, 2 gets sent to 4, we can just write it as 2, 4. So now, as an exercise, you can try and write the following two permutations in cycle notation. So these two, try to write them in cycle notation. So with this said, you now should understand what a cycle is, and so now we will introduce a pretty important definition that we will often use about the concept of cycles, and that is of the length of a cycle. So it is a pretty simple definition. Given a cycle that written in the notation that we have introduced above, a1, a2, a3, up to an, then we call the length of the cycle. And we call the cycle here, that we can denote with alpha, we often call it a cycle alpha of length n, or sometimes an n cycle. However, we will prefer to use the notion cycle of length n, also not confuse it with the concept of n cycles in algebraic topology, even though we won't use it here. So there's actually, you can call it whatever you want. So with this said, we now, well, at this point we know, we are a little bit accustomed to the notion of cycle, and we know how to decompose a permutation in cycles, but perhaps it might not be clear yet what a cycle actually is. And well, a cycle is just a permutation. And now we will see how we can write a cycle in this notation here, that we denoted up here, in the classical array notation that we are all accustomed to in this way. So we will see how we can do that. And secondly, seeing that cycles are actual permutations, we will see that decomposing a permutation in cycles actually means that basically writing them as a product of cycles, because of course cycles being permutations, they can of course we can take their product, and the product is the usual product between permutations that we have seen in the last video. So it's basically just function composition. So let's now take an example of a permutation. For example, 1, 2, 3, 4, 5. That sends 1 to 5, then 5 to 4, and 4 back to 1, and then sends 2 to 3, and 3 to 2. So the following permutation can be decomposed in the following cycles: 1, 5, 4, and then 2, 3. Well, it turns out that the following cycles can be written as the following permutations. So let's call cycle number 1, let's call it beta 1. Let's call this permutation sigma, and let's call this cycle beta 2. So beta 1 can be written as 1 gets sent to 5, then 2 stays fixed, then 3 stays fixed, then 4 gets sent to 4 gets sent to 1, and 5 gets sent to 4. So this is beta 1. On the other hand, beta 2 is the following. So 2 gets sent to 3, 3 gets sent to 2, and then 4 and 5 stay fixed. And now it turns out that sigma can be written as the product. So let's see, and let's actually check that it is indeed their product. So let's write the first permutation, which is 154, the cycle 154, and this is the following. And then we have the cycle 2,3, which is the following. Now, using the same method that we introduced in the last video to multiply permutations in array notation, let's see what the result is. So we start by 1. Okay, well, 1 here gets mapped to 1, but 1 going here gets mapped to 5. So in the end, in the result, we get that 1 gets mapped to 5. Now, 2 gets mapped to 3, but 3 here gets mapped to 3. And so in the end, 2 gets mapped to 3. And similarly, 3 gets mapped to 2. Then here, 4 gets mapped to 1, and 5 gets mapped to 4. And look at this. This is precisely the initial permutation that we wrote up there. So now you can convince yourself generally that this is valid in general for all permutations. So if you decompose a permutation in cycles, you can write it as a product of cycles. And now as an exercise, you can try and, for example, decompose into cycles the following 2 permutations. So the first one is sigma, defined by the following array notation, and the second one will be beta, and will be defined by this other array. And also notice that when in a cycle notation you have a cycle that basically just maps back to itself, then this is in the group of permutation, the symmetric group, this is just the identity permutation. And for this reason, sometimes when we write permutations as products of cycles, we omit them in the product. So with this said, we now ask a question. We have 2 questions actually. So the first one is there some benefit? So is it a proficuous, we could say, technique to decompose a permutation into cycles? And we will see that for certain types of cycles, it is actually proficuous. It is an interesting thing to do. They contain interesting information about the permutation. And so this is an affirmative answer to this question, and we will see later why. And the second one is, can we decompose each permutation into cycles? And we're now going to answer this question. This also turns out to be true, but in order to answer to this question, we need to prove a theorem, and we will now state it down here. And the theorem is the following. And actually, this theorem is a little bit stronger than what we have said here, because we will need to introduce a new notion of cycles. And well, if you're comfortable with sets, I'm sure you are at this point of the course. If you have 2 sets, then you say that they are disjoint if basically their intersection is the empty set. And in the same way, you say that 2 cycles, A1, A2, A3, up to AN, and B1, B2, up to BL. And well, we say that these 2 cycles are disjoint if they do not move any elements in common, meaning that the movements done by this permutation here do not in any way modify the elements that are moved by this other permutation here. So there's a pretty logical definition, we could say, in this context. So now we're ready to state the theorem. So we're now ready to state this theorem, and in particular, it says that given a finite set S, then every permutation of S can be written as a cycle or as a product of disjoint cycles. And so now notice that also here we say that generally a finite set, but given that, well, let's suppose that its cardinality is n. Well, then notice that the cardinality of S is n. By the definition of cardinality, there exists a bijection. So bijection, we can write it also as such. So for example, so remember that this symbol indicates a bijection from the set 1, 2, 3, dot, 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 up to n to S. And so since basically bijections between sets are the same, we will also introduce in a couple of videos maybe the concept of isomorphisms and homomorphism for groups. Well, it turns out that isomorphism in general in mathematics means mathematical objects being the same. And in this case, mathematical objects being the same with sets is given by applications that are basically bijections. And so in this case, we can treat S as just, we can consider it to be equal to 1, 2, 3, dot, 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 up to n. And in fact, we will do so in the proof of this theorem to simplify it considerably. So let's call our set again, by the considerations we made above, let's consider it equal to the following set 1, 2, 3, dot, 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 up to n, where n is of course a positive integer. Now, furthermore, suppose that sigma is a permutation of S. And here we would write sigma is in the symmetric group of S, but it looks a little bit weird. So we're just going to say, because we've chosen S to be the name of our set. Well, with this said, let's now choose an element of S. Let's call this element A0. Well, then we will select another element, A1, and this element will be equal to sigma of A0, meaning that basically the image of A0 under the permutation sigma. Then we're gonna define A2 as sigma squared of A0, which is actually also equal to sigma of A1. And then we continue like this iteratively. But since we are dealing with a finite set, we know that this succession that we just obtained, that for now we do not know yet if it will end. So let's call it a n, and then that goes from 0 to infinity. Well, then this sequence, we do not know yet if it has an end. But being as finite, we know that it must end at some point. In other words, there must be indices that we can call m and l. Given m less than l, we must have that there will be some repetition at some point. So we'll have am is equal to al. In other words, and this actually implies that at some point we will have a0 is equal to a, and let's call this in this index m, being a positive integer, it will be equal to am. A0, okay. Or writing it back with the cycle, or writing it explicitly with the definition we gave, with basically by applying over and over again the permutation sigma, we can write this as sigma to the m of a0. And then we have the following equality. But notice that what we obtain is precisely a cycle. In particular, it is the cycle a0, a1, a2, dot, 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 up to a to the m minus 1. And then a to the m minus 1, because sigma to the m of a0 is just sigma of a to the m minus 1, is just a0, meaning that sigma to the m minus 1 gets mapped to a0. And so we can visualize this as follows. So we start from a0, which is an element of S that we took, basically. Then we see to what element sigma maps it to. So and maybe we say that it maps it to a1, and this a1 is sigma of a0. Well, then we see sigma, where does sigma maps a1? It maps it to a2, which is just equal to sigma of a1, which is also equal to sigma squared of a0. And then proceeding in this fashion, we reach a point where this sequence ends. So it basically will repeat itself, of course, because here we have defined an infinite. We could go on, but it will just repeat. And so we reach a point where a to the m minus 1, which is just equal to sigma to the m minus 1 of a0. Well, then sigma maps this element to a of m, which is sigma m of a0. But being this just equal to a0, we get this actually just gets mapped back to the beginning. And so what we obtain is a cycle. And this cycle can be written in the following way. So far we have that our permutation sigma can be written as a product of this cycle here. Like this. And then we do not know if there are any other cycles. And so now we actually have two cases. So two cases. Case one is we have already obtained sigma, so meaning that sigma is just equal to a naught a1 dot 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 up to a to the n minus 1. And in this case, we have proven our theorem. And case 2 is that sigma is not yet, we could say, exhausted. We have not yet expressed sigma as a permutation. And so we need other cycles. So what can we do? We can just repeat the same process. We can take another element that we can call B naught in our set S, such that B naught is basically, well, I'm sure you will accept this little bit of abuse notation that I will make. And by this I mean that B naught is not moved by sigma as a permutation. Okay, this is all it means. And so, well, taking this B naught in S, then we will build another sequence just like that starts from B naught, then apply sigma to B naught, we get B1, and this is sigma of B naught. Then again apply sigma again, B2, this is sigma squared of B naught, up to another integer, because we will reach eventually an end. And that integer is, we will call it L. We reach BL to the minus 1, we apply sigma again, and we obtain, this is just sigma to the L minus 1 of B naught, and then we get BL. And as before, we will notice that we necessarily need to have that BL is equal to B naught. And so this maps back to itself, and this is actually a cycle. And so we will obtain another cycle that we can call beta, given by the following expression in cycle notation. And so far, our permutation sigma can be written as a naught, a1, dot, 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 up to a n minus 1, then b naught, b1, dot, dot, up to bl minus 1. And then, again, here we have the same problem. So it might, case 1, sigma is okay, so we already represented it. So we have our sigma and can be written as a product of disjoint cycles. In case 2 is we are still lacking some elements. In that case, we are proceeding in this way, and in the end, we obtain that sigma can be written as a naught, a1, dot, 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 up to am minus 1, b naught, b1, dot, 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 up to bl minus 1, and then other permutations that we can obtain by iteratively basically repeating this argument. And notice that this argument can be repeated a finite amount of ways, and then at a certain point we will exhaust the elements. Why? Well, because we're working with a finite set. Recall that we said that the cardinality of our set S, we required it to be a natural number, meaning that we required it to be equal to a finite set. And so for this reason, we know that this process actually has an end. And so by repeating this process, we obtain a representation, basically we could write this permutation sigma as a product of cycles. And these cycles are actually disjoint. Well, why? Because each time we perform this iteration, we suppose that the other element that we took was not changed by the other permutations. And so with this, we have concluded this proof. So with this said, we have now obtained a representation of a permutation in terms of disjoint cycles. So now let's make some examples to build our intuition. So for example, consider the permutation given by sigma, and I will just write the expression to save time. I will skip the process. Well then, let's see how we can write this in terms of disjoint cycles. So we notice that immediately the first cycle is 1 that gets sent to 2, then 2 gets sent to 3, then 3 to 5, 3 to 4, 4 to 5, and 5 back to 1. So the cycle in cycle notation is 1, 2, 3, 4, 5. And then the other cycle is 6 that gets sent to 7, 7 to 8, and 8 back to 6. So it's the following. And so here we have obtained an expression of sigma in terms of 2 disjoint cycles, namely 1, 2, 3, 4, 5, and 6, 7, 8. Let's now make another example. For example, let's call this sigma tilde, and let it be the following permutation. Let's do the same for sigma tilde. And here I'll do it faster because I'm sure you now can also do it faster. So we have 1 gets mapped to itself, but we have said that being this the identity permutation, we can omit it in the cycle notation. And then the next cycle is 2 gets sent to 3, then 3 to 8, and then 8 to 4, 4 to 7, and then 7 back to 2. And then the other cycle that we have is 5 gets mapped to 6. And so this is the cycle representation for sigma tilde. Now, I want to ask a question. So, is it true that this is equal to basically, what if we switch the order? I want to let you notice something. So let's do this. And now I ask, are these permutations equal? Well, you can try and compute yourself. And after you've done that, and pause the video until you've done that. And now that you have done that, I will actually give an answer. And that is, yes, they are equal. And now we also ask another question. Is it a coincidence or is it actually a general fact? It turns out that it's a general fact. And notice, be careful that this is not valid for all cycles. This is just valid for disjoint cycles. And I'm sure you can already intuitively understand why that is the case, because if a cycle does not influence in any way the elements of another one, then of course they will commute, because, well, the elements that are changed by a cycle will remain fixed in the other. And so switching the order doesn't affect how they change. But now let's state it as a theorem. And the assertion of this theorem is that disjoint cycles commute. Or in symbols, given alpha and beta disjoint cycles, alpha beta is equal to beta alpha. So let's prove it. So in order to prove this, let's write alpha in more extended notation as A2, A1, A2 up to AN, and beta as B1, B2, up to BL. And so again, let S be our set as before, 1, 2, 3, up to N. So now we want to show, in order for these permutations to be commutative, we want to show that for any x in S, we want alpha composed with beta of x be equal to beta composed with alpha of x. So in order to do that, we will divide the elements of, S into three classes. So the first one is the elements moved by alpha and fixed by beta. So notice that the elements moved by alpha are of course fixed by beta. So we could have omitted this because alpha and beta are disjoint cycles. The second class are the elements moved by beta and fixed by alpha. And the third class of elements are the elements fixed by both alpha and beta. And so let's see that for each element inside of these classes, actually these two cycles commute. So let's suppose that we have an element of the first class that we can call, for example, C. And we can use this Algebra notation, meaning that C is an S and respects 1. Well, now let's compute alpha beta and beta alpha of C. So let's start by alpha beta. Well, alpha beta is basically alpha of beta of C. But notice that beta of C, by what we supposed, is equal to C because B basically fixes it. And so this is equal to alpha of C. Now let's look at this other one. Here we have beta of alpha of C, but beta fixes alpha of C since alpha and beta are disjoint cycles. And so in the end, this is just alpha of C. And notice these two are equal. So this holds for the first class of elements. For the second class of elements, suppose that D is an S and also respects the condition 2. Well, then alpha fixes it this time. So let's again compute these two expressions. And so for the first one, we see that we have alpha of beta, of D, in this case, of D, but alpha fixes beta of D because alpha and beta are disjoint cycles, and so in the end we get beta of D. On the other hand, here down below we get that alpha fixes D, so this is just equal to beta of D, and so these two are equal, and this is also valid for elements of the second class. Now for the third class, let E be such element, then we know that both alpha and beta fix them. So alpha of V will be equal to E, and beta of E will be equal to E. And so what we will have in the end is that alpha beta of E, which is just alpha of beta of E, is equal to alpha of E, because beta of E is equal to E. But then alpha of E is again equal to E, and so we get E in the end. And by switching the order, we notice the same thing. So you get that this is equal to beta of alpha of E, but alpha of E is E, so this is equal to beta of E, and this is equal to E. And so this proves generally that the two disjoint cycles commute. So with this said, we have concluded another important part of, we could say, permutations and how they behave algebraically. And in the next video, we will prove some last very important results about permutations and maybe also give some more examples and work with them a little bit more practically.